Good morning, everyone. Thank you very much for attending this presentation today. In the next 30 minutes, I'll present the results of my research during my PhD at UT. The title of this presentation, as well as the title of the thesis, as was introduced previously, is Effects of Elastic Shear Modulus on Solid Liquefaction Modeling and Effective Stress Analysis. This presentation will be organized in the following way. I will start by first introducing the context and the purpose for this study. I will follow by a summary of the different approaches that can be used for liquefaction assessment. Later, I will present the stress density model, which has been the constitutive model I use for my research. And finally, I will walk through the different stages of my research and the results that were obtained, concluding with the key findings. As you may know, solid liquefaction is a phenomenon that started gaining attention from the engineering community after the Alaska earthquake in 1964 and the Niigata earthquake in the same year. Solid liquefaction is a phenomenon that produces severe damage and also extensive damage, which result in significant long-term impact in a community. This is the reason why we engineers need to assess this phenomenon rigorously. I will show some damage caused by solid liquefaction during recent earthquakes. So, for instance, various structures can be damaged by solid liquefaction. In this case, I'm showing now, you can see how the wastewater system was damaged. Also, lifelines can be interrupted due to liquefaction, and this may jeopardize the resilience of a community. The damage caused by liquefaction can come from different sources, such as lateral spreading or flow sliding. Also, the differential settlement can be produced by liquefaction. And finally, I will show some examples for an earthquake here in Italy, where the pictures correspond, two of them, to San Ejecta. Besides the damages I tried to exemplify with these pictures, we need to keep in mind that the ground motion at the ground level is going to be modified if solid liquefaction happens. So if we are trying to understand how our structures are going to behave, we need to understand that if liquefaction happens, their dynamic behavior is going to be affected as well. For liquefaction assessment, there are several procedures. Most practitioners prefer to apply the ones that are within the simplified method framework. It is relatively easy to apply. It requires the calculation of a factor of safety, which is the ratio between the liquefaction resistance and the seismic demand. The liquefaction resistance is obtained by empirical equations, where SPT or CPT data is input, and these empirical equations has been obtained from field case history data. Even though this is quite often used, there are many drawbacks in this procedure that are related to the fact that each layer is analyzed individually from each other, so the cross effect among them is not considered, as well as the dynamic nature of the problem is neglected. There are, as I mentioned before, there are other methods for liquefaction assessment, such as the use of hazard maps or energy-based approaches, laboratory and physical model tests, or physical measurements of the pore water pressure development during dynamic loading. Of course, there are also computational mechanical approaches. And within this framework, the seismic stress analysis is one that stands out for liquefaction assessment. This method can be loosely coupled or fully coupled. In the past, this type of approach was restricted to research or big projects, mainly because of the several laboratory tests that were required for the calibration of the material parameters. But in the recent years, a few constitutive models allows for their implementation using pre-calibrated sets of material parameters, and they only require CPT or SPT data, that is the same data that is required for simplified method approaches. With the advantage that we gain accuracy, we also can consider rigorously the dynamic nature of the problem. We can also evaluate the effectiveness of liquefaction mitigation measures. And finally, but not least, it can be implemented within the performance-based design framework. So keeping in mind this advantage and the possibility of using this approach using as input CPT or SPT data, my research has been focused on this approach. There are several fully coupled constitutive models. I've listed a few. Based on the literature review and the study of how this different constitutive model has been validated and verified, we decided to do the research based on stress density model, or in short, SDM. This is a constitutive model that has been around for 30 years and is extensively validated against case history, laboratory tests, and centrifuge, including centrifuge tests. So I will walk you through the main properties of this constitutive model. So STM is an elastoplastic constitutive model that has been tailored to model sandy solids, but in particular liquefaction. It is characterized by continuous yielding or vanishing of the elastic region. It combines isotropic and kinematic hardening plasticity. The strain increment direction is related to the stress state and the stress increment direction as well. It uses a modified hyperbolic stress-strain relationship and an energy-based stress-dilatancy relationship. On top of this, at the core of the constitutive equations, the state index is included. This is a parameter that allows to consider the combined effect of density and confinement stress. This is key for SDM because now a given sand can be modeled to considering any density and confinement stress, requiring only one set of material parameters. So SDM has, at the moment, two ways to calibrate this constitutive model. Starting for the more rigorous approach, which is based on a given sand, so one sand is going to be associated with a set of material parameters. SDM, I need to mention this before I keep going. So SDM has 15 material parameters, which can be grouped in 4 types: elastic parameters, reference lines, stress-strain parameters, and dilatancy parameters. These parameters, each of them is associated with a specific laboratory test. And for example, I have listed 3 different soils that has been calibrated in the past, in previous studies for SDM. In the recent years, a new calibration approach has been introduced. Instead of calibrating the material parameters on laboratory tests, the calibration is based on empirical equations that are within the framework of the simplified method. In particular, the Boulanger and Idris Liquefaction triggering relationships has been used for this purpose. From these equations, target liquefaction resistant curves that are now going to be used for calibration were developed. In the example that now is shown, there are 4 of them. They are in gray. They go from 70 to 140 QC1 and CS, and 70 is associated with loose sand, while 140 will be associated with the medium dense to dense sand. So in gray we have the target, and the open markers represent the simulations obtained with SEM. Besides calibrating the parameters against those liquefaction resistant curves, or in short Lrcs, also equations from the same reference were targeted to consider the effect that the confining stress has on the liquefaction resistance at different densities. The result of this calibration is a set of material parameters that is listed in the table that is shown in the last column, and also this equation that is now in red that relates the relative density to QC1 and CS. So now a user can apply effective stress analysis using stress density model, only having as input or CPT data with these 2 guidelines. This was the departing point for my research. So from now on, I will walk through the different stages of this particular study. The main focus has been a more rigorous modeling of the elastic shear stiffness. In STM, the constitutive equation that describes the elastic shear modulus is the empirical equation by Iwasaki and Tatsuoka, 1977. In this equation, our main focus during this study has been this parameter named A. This parameter is related to the effect that the soil has on the shear modulus. So A is going to affect the elastic shear modulus, and we are always talking here about relatively small strains because we are talking about elastic deformation. A is going to affect directly the dynamic properties of our numerical model, but indirectly, and now I would like to make a stop here and go back to what I mentioned before. In STM, during the modeling, each strain increment is divided in 2 components. On one hand, we have an elastic part. On another hand, we have the plastic part. So if we modify the parameter A, and hence we modify the elastic component, we are going to also modify the plastic part. So indirectly, the parameter A is going to modify the evolution of or development of pore water pressure, and also the shear strain development during cyclic mobility. And now I'm going to make a pause here because I would like you to notice that at the moment this research is started, we didn't have any guidelines to calibrate this aspect of the simulation. So at the second stage during this study, we scrutinized several laboratory tests to develop a criterion for calibration of this aspect of the simulation. So now I go into more detail. Let's start by how the parameter A was determined in this study. So the equation presented before was rearranged, and this allows to back calculate the parameter A from laboratory tests where the initial elastic shear modulus was measured. And here I want to highlight initial. So one of the requirements for selecting the test was that the strains were small, less than 0.001%, which means that the level of deformations were comparable with in situ shear wave velocity measurements. I forgot to mention something that required a lot of work, actually. I scrutinized 41 different sums at different densities and confinement stresses, and a total of 900 tests were used for this study. Once we have the value of A calculated for each of them, we calculated the average or mean and standard deviation. And for the next slides, I would like you to remember this value, the mean value, which is 709. So I will use that in the following slides. For now, I would like also to explain that in liquefaction problems, we are concerned about the behavior of the soil beyond what is called the volumetric shear strain threshold. Why? Because beyond that point, we start observing plastic deformations, and the shear deformation is associated with volumetric deformation. So in reality, we are not concerned about the properties, the initial properties, but we are more concerned about the value of A at a level of a strain corresponding to 10 to the minus 4 and beyond. So what we did was to scrutinize several laboratory tests where the modulus degradation curve was obtained for different clean sands. Now the markings represent the results from different tests corresponding to different sands, and the black line corresponds for reference to the Cardinale curve. In average, we observed that we had a degradation of 25%. So that leads to the next slide, where we combine the initial value with the graded 25%, and we obtain more or less a value, reference value for this parameter A that is related to the elastic shear modulus of 500. And this is going to be used in our simulations. And now I will make a pause here for this path of the research, and I will switch to another part of the study, which refers to the experimental evidence of a strain development during cyclic mobility. So, to include a general example, I decided to put this figure so you can see. Usually, entering cyclic tests the results are presented in this way. So we have the effective stress path on the right-hand side and the stress strain curve on the left-hand side. What I referred here, our interest was once the effective stress reduces and goes close to zero, we observe that there is a softening of the soil and larger strains start to develop. And now you can see here how cycle after cycle the strength increases. So we were concerned about this aspect. Okay, how far does this increase? What are the parameters related to this aspect of the behavior? So what we did was to replot all the results in the way that are now presented and now shown on the screen. So we measure the double amplitude shear strain cycle after cycle, and we focus on what happened during cyclic mobility, which is now the bottom curve that I enlarge here. So is this, I hope you, are you able to see the arrow here? Oh, good, thank you. So we focus our attention in this part of the simulation. We fitted linear relationships in two ranges, one from 1% double amplitude shear strain up to 5% double amplitude shear strain that has been the liquefaction criterion selected for this study. Now we calculate the slope of this line, and I will call it ratio 1 because it's shorter. And then the other part corresponds to beyond 5% double amplitude shear strain, and I will call it ratio 5. We studied, so now each test is going to be represented by these numbers. And we studied how these ratios were related to the cyclic stress and also to the relative density. We didn't observe any correlation between this ratio and the CSR, but we did observe the correlation shown now with the relative density. We fitted an average curve, and also we depict upper and lower boundaries. This helps us not for our calibration. For our calibration, now we have these lines that represent targets for simulations, numerical simulations. We did the same for the ratio 5, and actually the results were quite close to each other. We observed small differences as the relative density increased, and this is why I decided to plot all of them together. Once we had gathered and studied the results for laboratory tests available in the literature, we include that information in our simulations. To exemplify the effect that this elastic parameter has on element test simulations, I decided to include simulated Lrcs for Toyura sand, which is a reference sand in liquefaction problems. Toyura sand has a value of A of 250, and now to represent a generic sand, we are saying we want to have a value of 500, which is double this value. If I only modify this parameter, I observe an increment in the liquefaction resistance, which you can see now because the Lrcs are moved upwards, and then if we look closer to each of these points is associated with an element simulation. If we look closer, we observe also that there is a reduction in the maximum double amplitude shear strain that we can attain. This is detrimental for the numerical simulation because especially when we have dense sands, we couldn't achieve the liquefaction criteria that we have selected. And also, we know that then if we implement this, the results we are going to obtain are not representative or of the nature of the problem. So, to address these two requirements, we decided to introduce a small modification in SDM, which consisted of, okay, initially, I'm going to have a constant value of A of 500. At the beginning of the simulation, when the deformations are small. But then, instead of keeping a constant value as it has been done before, we are going to degrade this. When we reach a value of a single amplitude shear strain of 0.5%. So after this point, we start recording a cumulative strain, and we relate the degradation of A to this cumulative strain, which is a measure that increases cycle after cycle during this type of loading. Once the constitutive model was modified, we have to recalibrate it. And we did so using the first two criteria that were previously used when empirical relationships were used as target, but we also added the criterion obtained during this study that is related to observations in laboratory tests. The last column represents the set of material parameters corresponding to a generic sand. We also evaluate different empirical relationships to link the relative density to QC1 NCS. We decided on the Kubrinovsky et al. 2019 equation, and the ratio of Q and R was selected from Boulanger and Idris 2014. This is a comparison of simulation versus target Lrcs. The gray are targeted and the black corresponds to simulated with SDM. The simulations were performed with a vertical effective stress of 100 kilopascals, an initial stress ratio of 0.5. We also compared the results with the target curves that represent the effect of confined stress. Here, the accuracy was not as good as with the previous criterion, but we prioritized the first one. And finally, we compare simulations and test results. Once the results at the element test were satisfactory, we ran effective stress analysis. We did these simulations for 2 sites in Christchurch, and we input the Darfield earthquake, which produced, during that earthquake, those sites liquefied. So we knew that they liquefied. I just showing one example here. The comparison between the original and the modified version of STM was divided in 3 steps because we couldn't compare them directly. The original STM was implemented in one platform and the modified version was implemented in a different one. Let's start the discussion of the first step. So the comparison of 2 numerical platforms, which are Diana J and FLAG. Diana J is an implicit finite element program, while FLAG is an explicit finite difference program. They also differ in the way the pore water pressure is calculated. This has been key to identify the differences between the numerical results. And the last row is not related to differences in the program, but is related to the fact that STM has been implemented in Diana J for 3 decades. So it's extensively validated, as I mentioned before. So this is why we decided to use this implementation for our benchmark. So I just show a quick simulation here, comparison between FLAG and Diana J. I highlighted the layer that liquefied, so it's easier for you to see. At the bottom, you can see effective stress path and stress strain curve, while at the top, you can see acceleration history analysis, the input, the corresponded at the top of the element that liquefied, and ground surface. In general, the results are comparable with each other. There are a few differences that need to be highlighted. One of them is that in FLAG, larger deformations were observed at the liquefied layer, and also higher dilation spikes. And I will switch to the next because I'm kind of out of time. Okay. So one of the other differences was in the pore water pressure profiles. In FLAG, there was a faster and larger evolution of pore water pressure and smoother profiles that are associated with the numerical scheme. Then we compare the modified and the original version of STM using initial isotropic stress conditions. We did this because the previous version of STM was calibrated with those conditions. So for making fair comparison, we use that as the reference. Here, with the modified version, we obtain a smaller deformation at the liquefied position, and also even higher dilation spikes. This is an aspect that needs to be further studied because it produces higher peaks at the acceleration at the ground level, which are of course going to affect a numerical model if we are concerned about the behavior of the structure at that position. Finally, since the modified version was calibrated for an initial stress ratio of 0.5, which represents better free field conditions, that are the conditions of the field that were used for the development of the empirical equations. So that is the reason behind. Using anisotropic stress conditions, we observe a reduction in the high dilation spikes, and we also observe slower pore water pressure development and a reduction in the deformation at the liquefied layer. The reason behind this is because the anisotropic model has a smaller mean effective stress, which leads to a more flexible system. So now I will walk through the conclusions. This study, the purpose of this study has been to facilitate liquefaction assessment when CBT data is available to characterize the site of interest through the use of seismic effective stress analysis. The conclusions are divided in three, as it was the presentation. So the first stage was to determine parameters based on laboratory tests. The key here has been a representative value of A of 500 and curves to represent the strain development during cyclic mobility that were used as a criterion for calibration. The implementation of this information in the NSDM requires a small modification that is now shown on the screen. The recalibration of the model was based on these three criteria, and then we compared the results in the effective stress analysis, dividing the comparison in three. First, the effect of the numerical platform, flag and Diana J. The results were similar. A few differences were observed, such as larger deformations, localized as larger deformations at liquefied layers, also higher dilation spikes, and faster development and smoother pore water pressure profiles. The second step was to compare modified and original SDM. The conclusion here is that the modified version produces small deformation. That was expected because we have observed that in the elemental simulations, but also we observed higher dilation spikes, what we didn't expect, and this needs to be further studied. The last step was to compare the effect of anisotropic and isotropic confined stress. The use of anisotropic confined stress initial corresponds to smaller deformations and reduction of the dilation spikes. So these are a list of a few ideas or suggestions for future research. One of them is instead of taking an empirical equation to relate relative density to QC1 LCS, use our own equation so we can obtain better agreement with the three criteria that we have selected. Also, we have observed that differences were caused due to the pore water pressure calculation in flux, so maybe that could be reassessed in a different way. Also, further study is needed to compare the effect of this modified SDM. Either comparing with laboratory tests, including centrifuge tests, and finally, the use of different platforms to evaluate the modified version in different platforms. So, I'm sorry for the 4 minutes late. Thank you very much for your attention. And if you have any questions, I'll be here.
Very well. Thank you, Jemena, also for speeding up at the last part. So questions by the committee, Professor Elia.
Good morning. I'm from Politecnico di Bari, not from Naples. Don't worry.
My apologies.
No problem. Okay, thank you for the nice presentation, and I really appreciate the effort of this work to go towards the use of an effective stress-based analysis for these kind of problems in soil dynamics. I really appreciate your effort to implement the model and advanced elastoplastic constitutive model into a finite difference program, and all the issues that this may have caused and all the problems of the implementation and so on. And I strongly agree with you that we need to abandon the simplified procedures and move towards the effective stress-based simulations for these kind of problems. What I found a little bit confusing in your work are some small issues and then an overall path that you followed in your work. First of all, just very quick, I see that one of the parameters of the model is M, capital M, the critical stress ratio, which is 0.6, which means that the friction angle of the sun is something about 15 degrees, 16 degrees, which is something wrong for me, because M equal to 1.2 corresponds to 30 degrees. If M is the critical stress ratio that we have in mind, that means 6 sine of phi prime divided by 3 minus sine of phi prime in compression, then M equal to 0.6 means a very low friction angle, which is something strange for me for a sand. So I don't know if you...
If I have any comments about that?
Yes.
So I go back to very beginning, probably. So I may need to show 2 slides. Yeah, I'm seeing one of them here, so but they are tiny. Okay. Okay. So the way this has been calibrated is we departed from Toyota-san material parameters, and as you said, the parameter M is the critical stress ratio. So that, if we are very rigorous on that, it should be a value that is exactly the one measured. But the parameter M also affects the. Okay, now I'll go back to the beginning. Okay. It is also related to the stress dilatancy properties. So it's the value that the dissipation of energy took at the end of the test. So it's related to that aspect. So we modified it slightly to also achieve a good simulation regarding this second aspect. So it's not exactly that, it's slightly modified, but we didn't modify large, it's just within small ranges that we adjusted. So that, because then that helps us to achieve better simulations of the target Lrcs.
Okay. Probably you should call it in a different way, because this is not the critical stress ratio, probably. Otherwise, it means that the friction angle is very low.
Okay.
The main aspect, by the way, is that what I see is there is no discussion about the damping provided by the soil.
Yeah.
So you show us the G gamma curves, so the degradation of the stiffness with shear strain, but you never show us what are the prediction of the model in terms of hysteretic dissipation, so elastoplastic dissipation during the cycles, which is a crucial aspect in soil dynamics. But more importantly, even more importantly, I have another doubt that in my mind there is a clear distinction between elasticity and plasticity. So I agree that elasticity affects the elastoplastic behavior even for large strains where you have plasticity. But why don't you modify the hyperbolic part of the model to capture the degradation of stiffness with gamma instead of reducing the elastic part of the model, so the elasticity, which may control the beginning, the initial profile, but the shear stiffness degradation should be controlled by plasticity more than by elasticity. In fact, in your elasticity, I agree that should degrade a little bit when during the cycle, during the unloading part may have a lower elastic stiffness, but then the main reduction of stiffness at large strains should be given by the elastic part of the model. And in any case, you start from looking at the laboratory test in terms of capital A and take an average value. And I agree that you want to calibrate the model with simple, for a soil deposit with simple in situ test, but there is a big misinformation. What is the VS profile of your deposit? The VS profile should affect capital A, so you should use CPT for relative density, friction angle, the strength of the material, and VS for the elastic part of the model. So for capital A, this is what we think in soil dynamics.
I identified 3 questions. I hope I can address all of them. If I miss some part, please let me know. The first one was regarding why I focus on the elastic shear modulus degradation curve, but I didn't study other aspects of this.
Because this G gamma curve is the overall effect of elasticity and plasticity.
Yeah.
Okay, so the beginning, the anchor point may be controlled by elasticity, but the degradation is controlled by plasticity.
Yeah. So, and you asked me about the dissipation of energy, right?
Yeah, there is no damping curve.
Yeah, so, okay, as far as, so that aspect was not considered for calibration, but I know about other studies where the damping curve has been used for calibrating STM, but that concerns more to the non-liquefiable layers, which, so in fact, I didn't present that or explain that part because it was not part of my work. But the non-liquefiable layers were calibrated based also on the damping curves. Okay. Then you asked me why to develop larger strains I modify A instead of modifying parameters associated with the plasticity. Well, the issue with soil liquefaction is that the behavior changes completely. We start with one material and we end with a completely different material. So that was the reasoning, the physical reasoning behind degrading also the value of A, where we expect that once we achieve liquefaction, the contact between the granular soil is loose, and now we have a different material. So that was the justification behind the fact that we degraded the value of A. Yeah. So, and I missed the third one.
The use of a VS profile to calibrate.
Okay, thank you. I saw that you were nodding, and so you were interested in that part too. for the calculation of A, and I will go back to that slide. Here. So I understand that you have the measurement of shear wave velocity profile. You want to implement that in your modeling, but for calculating calculating the value of A, we also needed measurements of the void ratio, and we also the mean effective stress you can calculate it from the site, but the void ratio you may take samples. So that's why we follow the steps through laboratory tests instead. Now, if you have BS profiles and say, okay, now my soil has this value, and I want my model to represent this, well, this is going to be a little tricky because the value of A, as it was shown through the presentation, it not only affects the elastic properties, but it's also associated with other properties. So I do not recommend to change. I mean, you can do it, but you have to recalibrate all the parameters.
Yeah, but in your sorry, I go on. Your just last question. In your last application of a soil deposit, 20-meter soil deposit, you have a CPT test, okay,
yes.
And you calibrate everything against one CPT test. It means that that soil deposit, whatever VS profile it has, you just need one CPT test, but you may have the same CPT test and different VS profile, and the propagation of the wave into the soil deposit is completely different.
Yeah. Well, here is, so the modeling is a compromise of different aspects. So we have tried to do our best to have a well-represented elastic shear modulus, but we are not able to compromise other aspects of the simulation.
Thank you.
Okay, so another question from the committee, yes.
Okay, okay, thank you for quite interesting presentation. I have so many questions,
wow.
But Gaetano already asked many of them, so I will skip it. In what is interesting, Miško Čubrinovski actually started his career at my institute. Now that I'm working at ISIS, for a long time he was working at ISIS, then he moved to Tokyo and now in New Zealand. So I know quite an answer about Gaetano's questions. First of all, Miško doesn't believe so much in VS velocity, so it doesn't matter. So quite interesting question. I will skip all these answers, replies that you give to previous questions. First of all, why did you choose single parameter in order to explain or somehow to avoid all other parameters? Can you choose A, B, and C, or only A to take into account many effects that has on the shear modulus? Only one parameter, A.
Well, that's the parameter that relates to the type of soil. So what we wanted to do was to obtain a value that represents a generic sand. So now, okay, that's helpful because this is the distribution of the data, and it shows that we have a big dispersion. So the effect of the soil, even when we selected clean sands, normally consolidated, we even have a big dispersion. So we acknowledge that, but at the end of the day, we had to make a decision. And you asked me why this parameter and not others. The constitutes the equation of okay. So it was already this equation. So the effect of the void ratio and mean confining stress was described by this, and the only parameter related to the soil is the parameter A. I don't know.
Okay, yeah, okay. Just be careful when you're comparing different empirical formula, because this 1977, Iwasaki and Tatsuoka, that Toyota sand at that time was quite different than Toyota sand that Miško used in the 90s. And it's quite different than Toyota sand using in the 21st century. So just because Toyota is not always standardized, it should be standardized sand, but it's quite different material parameters. Miško has one paper about that, but anyway, it's okay about that. So I will and back to the questions of Gaetano. What he was thinking is that Vs as a parameter is much better representing the shear modulus. It's actually directly connection. And when you have a Vs, it is much more related to the elastic or shear modulus at low strain. Because as I see, for a parameter, you choose little bit large shear strain in order to calculate, to get values for A, because when we say low strain, we mean 10 over minus 4 shear strain, which is quite small, and it's very difficult to get these small strain parameters from laboratory tests. There are only few laboratory tests that can measure such a small quantity. So
yeah, we were careful about selecting the tests.
you should choose on-sample transducers in order to calculate.
We did that.
So okay, I know. So okay, then just to be careful about that. And the final question, the last, I cannot catch the soil profile. It is in Christchurch.
Yes.
Okay, and it is a more or less single layer, or is it with other layers, non-liquefiable, liquefiable layers all over?
So, okay, I don't know, maybe I can enlarge. I don't know, because maybe the text is very small in order to fit the information. So the lower layers are non-liquefiable, and the top, more or less 10 meters are liquefiable.
But this is more or less ordinary. Did you check to change the layers, for example, to have non-liquefiable layer above, let's say, 5 meters in order to see what will happen in the upper layers after the non-liquefiable layer?
No, I didn't know that.
Okay. Miško did it, but okay.
Yeah, no, I know that he considered the cross effect of
and it has this drawback that you mentioned for the simple,
exactly.
Back to the question of Gaetano, because these simplified methods cannot catch those interactions between the layers,
exactly.
non-liquefiable layers. Thank you very much for quite interesting.
Thank you very much.
Thank you, Vlatko. We have exhausted our time for discussion. Thank you again, Jemena.